the close. So given that B is the unit ball, right? Unit sphere, unit ball, kind of go back and forth with that terminology. It works in both cases, but you want to just kind of, be mindful that there's more than one. Like, I mean, ready for the most idiotic thing that I'll ever say. Be mindful of the fact that there's more than one way to say something. So ball, sphere mean the same thing. Right? It's not like a special case or anything like that. Right. So just trying to clean up my screen here. So given that B is the unit ball, so unit sphere, defined as x squared plus y squared plus z squared less than or equal to 1, was basically saying a filled in sphere with radius 1. Evaluate this triple integral. All right. So if you kind of look at it and compare it to what we had done previously, we could look at it in rectangular coordinates, in which case this would be dx dy. Let me get that to be a little thicker. Dx dy dz or some other permutation of that. We would have our x squared plus y squared plus z squared over some appropriate bounds particular to x, y, and z, which is why we just leave it b for bounds. All right. We're going to have some particular bounds associated with that triple integral, right? But we don't want to go too crazy figuring out what those bounds are, because we're right about to kick it over into spherical coordinates, right? And so when we do that, the first thing we're going to do is replace the dx dy dz, right? That's going to be replaced with a rho squared sine phi d rho d phi d theta. All right, that formula again, right at the top of the page, you have some function, and then the rho squared, which somebody submitted the typo, and I appreciated that. That p there is a rho. Sine phi, rho squared sine phi d rho d phi d theta. All right. So we're finding the triple integral of this multivariable function over those x, y, z bounds. All right. We do know that this is the same as saying rho squared. All right. So then the only thing that would remain is figuring out the bounds that are appropriate to this. All right. Now this is a unit ball of, filled in regardless, doesn't matter whether it was filled in or not. You're still going to find the volume contained by that unit ball over that appropriate interval. So let me move this down a little bit. So my first set of bounds is going to be related to rho. And I think it would make sense if you mark up the diagram. I know it's kind of hard to see. I put two of them there just so you can get two different perspectives. One of them is your ordinary three-dimensional perspective, and the other is the XY plane, or at least it's trying to be. So I'll just darken it in, X, Y, Z. If we're thinking in terms of some kind of movement theta, I'm sorry, not theta, phi from the z-axis, you could make a case that it goes all the way around, but you could also make a case that it only goes halfway. But before we even get to that, let's talk about the rho. The rho is going to go out as far as 1 unit in any direction, definition of a radius. So regardless of which way I go, it's still only going to have a value of 1. Right, the smallest value rho would be equal to 0. So I think it makes sense that we would call the bounds for rho 0 to 1. But for the phi, we got to start thinking about how we can kind of manufacture this whole volume. Right, so that phi, like I said, it could go all the way around. Now the positive x direction is over here, so I really should kind of think about going this way. So if I want to get down to the x-axis, for example, from the z-axis, that's a movement of pi over 2 radians. If I want to get to the negative z-axis, that's another pi over 2. Now, in a perspective sense, it could be, like I said, it could be pretty tricky. Here's my negative x. If I want to get back to the negative x-axis, that's another pi over 2. If I want to go the whole shebang, the whole distance, I'd have to go an additional pi over 2. So it's a total of 2 pi all the way around, which makes sense. But maybe I don't want to go all the way around. Maybe I only want this piece. All right, so just this component. Because if you sweep through one semicircle and then spin that semicircle around based off of the theta being allowed to go from 0 to 2 pi, then you cover all the volume, right? Another way to handle it would be to say, well, maybe I only want to go pi over 2. That would get me the first really octant, well, border of the first octant, depending on how far I went in terms of theta. Now that actually brings us to the other diagram. I got my axes kind of backwards, but it doesn't make a difference. The whole idea is it was supposed to be in the XY plane. I just kind of settled for anything that looked kind of right. So it's YZ, but it's really supposed to be XY. All right. So I'll take it as a typo. Because it is, you know, but you can all benefit from this. So this would represent the XY plane. And so from the sense of the XY plane, I'm starting at 0 and going all the way around to get to 2 pi. All right. Now there's two schools of thought on that. One is you're visualizing that distance really in kind of a sector that's being created by the movement from the z-axis down to the x-axis. That's sweeping through a quarter turn, sure, but it's creating a 90-degree arc that when spun around the other way, if you visualize that, that's going to give you a semicircle. I'm sorry, a hemisphere, the top half of the sphere, right? The spinning, so dropping it down and then spinning it around. So drop it down, spin it around. The spinning it around part is the XY plane. That's the 0 to 2 pi. The dropping it down, that's the pi over 2. Now it is possible you could say, so that would be a hemisphere. But if I wanted to drop it all the way down, so instead of going positive z to positive x, maybe positive z to negative z. That sweeps through a semicircle, right? That's pi radians. But then if you take that region that you just created, which would be a semicircle, and spin it around, that's the axis, based off of the theta value going from 0 to 2 pi, you would get the entire sphere, right? So it kind of makes sense that that's what we would do. So 0 to pi, 0 to pi, 0 to 2 pi, that would get you the whole shebang. But if you went 0 to pi over 2 and went all the way around, you just have to double, you know, I was going to say double your triple integral, which is just dangerous. It's going to sound weird. So I'll say instead, multiply your triple integral by 2. Right. So what we just got here are the bounds for the unit sphere, this piece. This part is related to the multivariable function, which we're integrating over that interval. So just think about how we talked about mass and density and stuff like that. we're incorporating an additional dimension, right? So we're not trying to find the volume under x squared plus y squared plus z squared in 3 dimensions. We're actually incorporating that as a 4th dimension, just looking at it as a 4th dimension to this whole thing. It's just, it happens to be represented as a multivariable function, x squared plus y squared plus z squared. Okay. So then in the process of solving this or evaluating it, we're going to clean it up. Let me just shrink it down so I have some room. Not much to clean up, which is good. We have rho to the 4th sine phi, not sine, yeah, sine phi d rho dp d theta. We're going to evaluate it over 0 to 1 first. That's those p's. Then we'll take care of the rest of it. 0 to pi, 0 to 2 pi. Now, there's plenty of applets out there that'll show you what the multivariable function looks like in spherical coordinates and all that. So I'm in the process. I know I mentioned it last class, but when I finally found the GeoGebra applet that I created previously for spherical coordinates, I was very underwhelmed by my own work to the point where I'm like, I gotta do this over. So I'm still efforting it. So more on that later. So 1/5 rho to the 5th sine phi over the interval of 0 to 1. All right. So we're looking at 1/5 sine phi. All right. Plug in a 1 for phi, 1 for rho, and you get 1/5. Not doing anything with the phi at this point. Plug in a 0 for rho, that's going to zap away. So this is what we're integrating now with respect to phi and then with respect to theta. All right. So it's at this point where hopefully it's up to you, because the computations aren't that bad either way, but hopefully you're considering doing it in Desmos. All right. So we're looking at a dp. This is over the interval of 0 to pi. And then once we handle that, 0 to 2 pi d theta. Now, there is a way, like I mentioned this last time, there is a way to do it all in one shot in Desmos, as long as you have consistency with your variables, it'll handle it. The issue is that if you want to get the phi and the theta in there, you got to do it on a keyboard, or at least that's been my experience. Otherwise, you're using X's and Y's, and the variables are easy to get confused. If you don't get the parentheses just right, things fall apart. So what I've just kind of accepted is I'm just going to do it one at a time, and then take the answer if it's clean enough and put it in the other integral. So here's my 1/5. That's a 15. I want 1/5. We'll say sine of x, just for convenience, and dx. All right, so it's a clean 0.4, so I can work with that. All right, so enter function integral 0 to 2 pi. I mean, it's constant, so you probably already can figure out the answer in your head, but I'm just going through the process here. All right, so 0.4. And then we'll say dx again. And you get this. But you know it's a multiple of pi. So it's a question of whether you want to round it or you want to just say, okay, well, I know it's 0.4 times 2 pi, so it's 0.8 pi, or 8/10 pi, or 4/5 pi, however you want. But it doesn't matter to me. Right? So what a lot of people will do is they'll take this answer and divide it by pi, because they know pi is going to be part of it, and they just slap a pi on whatever they get. That's fine too. you know it's 0.8. So then you get rid of this and you say, okay, well, it's 0.8 pi. So therefore 0.8 in fraction form, simplest form, 4/5. So 4 pi over 5. But like I said, I'll allow the decimals as long as you round them in a reasonable way. All right. So, if you call this 3, I'm not going to be happy, but 2.51, 2.513. A good rule of thumb is 3 significant digits, the first 3 non-zero decimal places. That's reasonable, right? But if you wanted to, you can slap an integral around this whole thing. Oh, wrong one. Zero, 2 pi. Something else. Yeah. So I just changed the variable up, made it a dy instead of a dx. It'll do it. It just it's kind of finicky, right? So the way I do it on Desmos is pretty much the way I do it on paper. I think the way most people do it on paper is you integrate the first one and then take the result and plug it into the second integral and then go from there. It's a pain to type in the phis and the thetas, so I use x's and y's just to make it simple. And if this thing would let me expand, you can see, but there's a dy at the end. You can see it there. All right. So parentheses around the innermost integral. Well, all those parentheses, it gets crazy the more complicated the expression is. With the outer integral going from 0 to 2 pi, it gets you the answer all in one shot. All right. But sometimes that's more complicated, especially if you find that you're just getting errors and you're consistently getting the wrong answer. It takes more time to try to figure out where you went wrong than it does to actually do it out by hand. Right? So let me stop that recording.